My name is Trevin Detwiler, and I worked with Keegan Finger and Daniel Viscarra, two other students at Drake University, on problem B, looking at the bike throw. So the first question is, what is this trying to model? Near a finish line during a bike sprint at the end of the race, a biker can choose to throw their bike forward, giving a little bit of a push in order to gain some extra distance to reach the line first. So the consequences to consider in this is first, there's a temporary gain of distance. While there's a gain of distance, there is also going to be a deceleration during the push due to air resistance, which gives us a small window of success for pulling off this strategy. So the main question we want to ask in this model is just how precise does the timing have to be in order for using a bike throw to be effective?
So a strategy for answering this question was, first off, we needed to build a model that would accurately portray what is happening at the end of such a race in which the riders would be implementing the bike throw into the strategy. So we decided to go for conservation of momentum and an applied force on this system. Momentum is given by mass times velocity. So if we consider the mass of the rider and the mass of velocity of the bike to be one, essentially, as they're traveling along, and to get their momentum, we also include their velocity, since they're going as one kind of block. Next up, we implement conservation of momentum, which gives us that the derivative of such momentum is going to be 0, from which we can get MA, which some of you might recognize as just the net force. And from here on out, we can determine what forces would be in play here, giving us a deeper model that can portray different forces interacting with the bike and the rider. Here we have again, how this differential equation would look like with the net force on the left-hand side of the equation. So now we will try to find what the net force might look like in practice. So here we have, again, the same equation. The net force is equal to the derivative of momentum, which we have on the right-hand side of the equation. Now, what might the net force look like? First off, on the left, we implemented a term that consists entirely of what the throw, that's why it's t sub t, the throw as a function of time might look like. So as the throw is happening, what would this force look like? The force of the biker physically pushing the bike forward to gain this forward this advantage at the end of the race. Next up, the second term in the net force comes from the fact that the rider is experiencing drag due to air resistance. So all those terms, we have density of air and other terms that represent the characteristics of the drag that the bike will be experiencing. And finally, the last term is it represents the biker's pedaling. So putting this all back together, we just add the net force back into our original equation and put it all on the left-hand side of the equation, and that is what the equation would look like. And this is the basis of our model for the next couple slides.
So some assumptions we're going to be making about this model. We are assuming that while the bikers are at sprint, the drag force is exactly canceled out by their pedaling. That is, that they'll be moving at a constant velocity. Next, we assume that the axle friction is negligible and that the wheels remain in contact with the ground. That way, any forces that are acting on the ground will slow it down, and that we assume that the wheel and the axle have a negligible force and don't show up in our model. We also assume that we are at standard temperature and pressure. This assumption comes from kind of empirical data on cyclists as a whole. So professional cyclists tend to stay around 70 kilograms. And there's actually a requirement for in cycling competitions that a bike has to be over 6.8 kilograms. So we're going to use 7 kilograms for this model. Next, we have the drag coefficient and the cross-section used for drag. This comes from the paper denoted down below, which gave us a cross-section of 0.481 and a coefficient of 1.33 for drag. Next, we make an assumption on how fast the bikers are moving at that sprint velocity, at which point we're going to be implementing our model when they do the bike throw. And finally, for the force due to drag, we have to also note the density of air, which is 1.204 kilograms per meter cubed. So what do our results look like when we apply these assumptions to our model?
So the first thing we have to take a look at is how this force is going to change over time, because we can't assume a constant force when we're doing this bike throw. So we examined a few different force curves, a linear in the blue, quadratic in the red, logarithmic in the yellow, Gaussian in purple, and then we also did some empirical testing on our own, which is shown in the green here. So all of these are scaled to go from 0 to 1 over our time interval. So this is spread out so that it's a little bit easier to see. But over the time interval that we choose, that this throw is taking place in, the force will ramp up from 0 to 1 following these curves, and then we'll ramp down from 1 back down to 0. So taking a little bit of a closer look at this empirical force curve, we see that over on the left here, it very closely approximates a Gaussian at the beginning, but we also see this negative acceleration region, which is going to be a deceleration of our bike towards the end. So it's not purely acceleration, but we do have a deceleration portion as we start to reach the full extension of our arms. So looking at some results, keeping the force curves on the left, the colors do match up. So on the right here, we can see the relative position of the bike with respect to the rider over time. So a positive value in this is going to be the bike being a little bit farther ahead than it would be normally. A negative value is going to be behind where it would be normally. So we do see a sharp increase and then an even steeper decrease in our position. That decrease is due to the drag force on our biker. So if we take a closer look, we can find where the peaks line up in this blue line, and this is approximately 0.2 seconds. So that's when the biker is going to want to start the throw so they get the maximum distance gained. And then we can look at those distances gained for each of these curves, which I'll run through real quick here. This will become more important in our analysis later on. So for each of these curves, we see a slight increase. So with our empirical data being significantly better, which is scaled by 10, I should mention. So just decrease so that it all fits on the same plot. Another thing we looked at is changing the hand positions. So we said 0.2 meters or 20 centimeters was the extension you could get keeping your hands on the handlebars. 0.4 was putting your hands on the stem of the bike. And 0.6 would be putting your hands on the seat to get a full 60 centimeter expansion or extension. So for linear here, we don't see any change, which is quite interesting and shows that linear is not a good fit for this force curve. For quadratic, we see a slight increase in our change here. For logarithmic, we also see a very slight increase on the left. And then for Gaussian, we see an increase. So clearly Gaussian is going to be the best way to look at this, which is also confirmed by our empirical data. So in conclusion, what can we tell from our model? So the first thing is, when should the rider stop pedaling and start to shift their weight backwards to throw their bike forwards? So if we assume 18 meters per second over 0.2 seconds, they would travel 3.6 meters in that time. So they should start throwing backwards 3.6 meters before the finish line. The effective time interval is just the area from 0 to 0 on our relative position curves. So that's going to be an average of 0.653 seconds. So really only about half a second to do this effectively. And then the maximum amount of time that can be made up is just the distance traveled divided by the velocity, with an average of 4 times 10 to the negative 5 seconds. So you have to be really close to the start for this to be effective. Just like to quickly acknowledge SIMIODE and Cubes for putting this together, as well as our coach, Dr. Becklin, for preparing us very well during our differential equation class last year.